National Electrical Code permits derating conductors when multiple current-carrying conductors are present in a raceway cable or directly buried in the earth. This derating is necessary to prevent overheating of the conductors and ensure the safety and reliability of the electrical system. In the scenario with 920 amp circuits using #10 THHN conductors and a 2-inch conduit, the initial step is to determine the allowable ampacity of the #10 THHN conductor. According to the NEC, #10 THHN conductors typically have an allowable ampacity of 40 amps when operating at a temperature not exceeding 90 degrees Celsius in dry and damp locations. However, this value needs to be adjusted based on the specific installation conditions. The primary factor affecting the ampacity is the number of current-carrying conductors in the conduit. When there are more than 3 current-carrying conductors in a raceway, the NEC requires that the allowable ampacity of the conductors be derated according to Table 310.15 CON or its corresponding table in the applicable edition of the NEC. For 4 to 6 current-carrying conductors, the derating factor is 80%. For 7 to 9 current-carrying conductors, the derating factor is 70%. For 10 to 20 current-carrying conductors, the derating factor is 50%. And for 21 to 30 current-carrying conductors, the derating factor is 45%. Finally, for 31 to 40 current-carrying conductors, the derating factor is 40%. In this case, with 920 amp circuits, each circuit has 1 current-carrying conductor in the conduit. This results in a total of 9 current-carrying conductors. According to NEC Table 310.15 CON, the derating factor for 7 to 9 current-carrying conductors is 70%. Therefore, the allowable ampacity of the #10 THHN conductor must be reduced to 70% of its original value. The calculation is as follows: 40 amps multiplied by 0.7 equals 28 amps. This means that, after derating, each #10 THHN conductor can safely carry 28 amps. Since each circuit is protected by a 20 amp circuit breaker, the derated ampacity of 28 amps is sufficient. In this case, you could install 9 20 amp circuits using #10 THHN conductors in a 2-inch conduit. The NEC provides guidelines for conduit fill, which limits the number of conductors that can be installed in a conduit of a given size. These guidelines are intended to prevent overheating of the conductors and to facilitate the pulling of conductors into the conduit. The NEC specifies the maximum allowable percentage of conduit cross-sectional area that can be occupied by conductors. This percentage varies depending on the number of conductors in the conduit and the type of conduit. For example, for 3 or more conductors in a conduit, the maximum allowable fill is typically 40%. To determine whether the conductors will fit in the 2-inch conduit, you must calculate the cross-sectional area of each conductor and the conduit and then compare the total conductor area to the allowable fill area of the conduit. Firstly, find the area of the #10 THHN conductor, including insulation. Consult the NEC Chapter 9, Table 5 and refer to the Conductor Properties table. According to this table, the approximate overall diameter of a #10 THHN conductor is 0.131 inches. To calculate the cross-sectional area, use the formula for the area of a circle, which is pi times the radius squared. The radius is half of the diameter, so the radius of the #10 THHN conductor is 0.131 inches divided by 2, which is 0.655 inches. The area is then pi multiplied by 0.655 inches squared. This calculates to approximately 0.135 square inches. Secondly, calculate the total area of the conductors. Since there are 9 #10 THHN conductors, the total area of the conductors is 9 times 0.135 square inches, which equals 0.1215 square inches. Thirdly, determine the inside area of the 2-inch conduit. Consult NEC Chapter 9, Table 4, which provides the dimensions and percentage area of conduit and tubing. According to this table, the inside area of a 2-inch Schedule 40 PVC conduit is 3.356 square inches. Finally, calculate the allowable fill area and compare. The maximum allowable fill for 3 or more conductors is 40% of the conduit's inside area. Therefore, the allowable fill area for the 2-inch conduit is 40% of 3.356 square inches, which equals 1.3424 square inches. Comparing the total area of the conductor's 0.1215 square inches to the allowable fill area of the conduit 1.3424 square inches shows that the conductors will fit comfortably within the conduit. In summary, with 9 20-amp circuits using #10 THHN conductors in a 2-inch conduit, the #10 THHN conductors must be derated to 70% of their allowable ampacity. After derating, each conductor can safely carry 28 amps, which is sufficient for the 20-amp circuits. The conductors will fit comfortably within the 2-inch conduit, as the total area of the conductors is less than the allowable fill area of the conduit. Remember that derating should not be applied to the grounded or equipment grounding conductors. These conductors do not contribute to the heating of the raceway and are not subject to derating. The specific requirements for conductor ampacity, derating, and conduit fill can vary depending on the local electrical codes and regulations. Always consult with a qualified electrician or electrical engineer to ensure compliance with all applicable codes and regulations. It is essential to note that the derating factors specified in Table 310.15 cone of the NEC are based on the assumption that the conductors are installed in a raceway or cable where heat is not readily dissipated. If the conductors are installed in a location where heat can be readily dissipated, such as in free air, the derating factors may not be necessary. In addition to the number of current carrying conductors, other factors can affect the ampacity of conductors. These factors include the ambient temperature, the type of insulation, and the presence of other heat-generating equipment. The NEC provides guidance on how to adjust the ampacity of conductors to account for these factors. For example, if the ambient temperature is higher than 30 degrees Celsius, the allowable ampacity of the conductor must be reduced according to Table 310.15 bone or its corresponding table in the applicable edition of the NEC. Similarly, if the conductor is installed in a location where there is other heat-generating equipment, the allowable ampacity of the conductor may need to be reduced to prevent overheating. The NEC provides tables and guidelines for calculating the appropriate derating factors for these situations. The NEC also specifies the requirements for conductor identification. Conductors must be clearly identified to indicate their purpose and voltage. This is typically done by using color-coded insulation. For example, the NEC requires that the grounded conductor be identified by a continuous white or grey outer finish. The equipment grounding conductor must be identified by a continuous green or green with one or more yellow stripes outer finish. The ungrounded conductors must be identified by a color other than white, grey, green, or yellow. The specific color coding requirements may vary depending on the voltage and type of system. The NEC also specifies the requirements for conductor splicing and termination. Conductors must be spliced and terminated in a manner that ensures a reliable electrical connection. This is typically done by using listed connectors and terminals. The connectors and terminals must be properly sized for the conductor and the application. The NEC also provides guidance on the proper techniques for splicing and terminating conductors. It is important to follow these guidelines to ensure a safe and reliable electrical connection. The NEC is a comprehensive set of standards and guidelines for electrical installations. It is essential for electricians, electrical engineers, and other electrical professionals to be familiar with the NEC and to follow its requirements. Failure to comply with the NEC can result in serious electrical hazards, including fire, shock, and electrocution. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. It is important to stay up to date with the latest edition of the NEC and to understand its requirements. The NEC is available for purchase from the National Fire Protection Association and other organizations. It is also available online through various subscription services. In addition to the NEC, many states and local jurisdictions have their own electrical codes and regulations. These codes and regulations may be more stringent than the NEC. It is important to be familiar with the electrical codes and regulations in your area and to comply with their requirements. Compliance with the NEC and other electrical codes and regulations is essential for ensuring the safety and reliability of electrical installations. Always consult with a qualified electrician or electrical engineer to ensure that your electrical work is done safely and in accordance with all applicable codes and regulations. Furthermore, understanding the specific application of THHN conductors is crucial for ensuring safety and compliance with electrical codes. THHN stands for thermoplastic high heat resistant nylon coated. These conductors are commonly used in electrical wiring due to their excellent resistance to heat, moisture, and abrasion. The nylon coating provides added protection against damage during installation. The temperature rating of THHN conductors is typically 90 degrees Celsius in dry locations, 75 degrees Celsius in wet locations, and 75 degrees Celsius when exposed to oil or coolant. This high temperature rating allows THHN conductors to carry more current than conductors with lower temperature ratings. THHN conductors are available in a variety of sizes ranging from /14 AWG to 1000 kcmil. The appropriate size of conductor depends on the ampacity required for the circuit. The NEC provides tables that specify the allowable ampacity of conductors based on their size, insulation type, and installation conditions. THHN conductors can be installed in a variety of raceways including conduit, cable trays, and wireways. The raceway provides physical protection for the conductors and helps to prevent overheating. The NEC specifies the requirements for raceway fill, which limits the number of conductors that can be installed in a raceway of a given size. THHN conductors are commonly used in residential, commercial, and industrial applications. They are suitable for both new construction and renovation projects. THHN conductors are a versatile and reliable choice for electrical wiring. However, it is important to select the appropriate size and type of conductor for the application and to install the conductors in accordance with all applicable codes and regulations. For circuits with sensitive electronic equipment, it may be necessary to use shielded THHN conductors. Shielded conductors have a metallic shield that helps to reduce electromagnetic interference. This can improve the performance of electronic equipment and prevent data loss. THHN conductors are also available with a variety of special features such as low smoke, zero halogen insulation, and sunlight resistance. These features may be required in certain applications. Low smoke, zero halogen insulation is designed to minimize the release of toxic gases in the event of a fire. Sunlight resistance is important for conductors that are exposed to direct sunlight. When working with THHN conductors, it is important to use the proper tools and equipment. This includes wire strippers, crimpers, and cable cutters. It is also important to wear appropriate personal protective equipment such as gloves and safety glasses. THHN conductors are a valuable component of modern electrical systems. By understanding their properties and applications, electrical professionals can ensure that their installations are safe, reliable, and compliant with all applicable codes and regulations. When working with electrical systems, always follow safe work practices. This includes energizing circuits before working on them, using insulated tools, and wearing appropriate personal protective equipment. Electrical work can be dangerous, and it is important to take precautions to protect yourself and others from harm. This explanation should provide a clearer understanding of derating THHN conductors and conduit, with practical examples and references to the NEC. Always refer to the latest edition of the NEC and consult with qualified professionals for specific applications and local requirements.